We've been doing carbon projects over the last year, soil carbon projects that is, and we've currently baselined about 17,000 hectares. And looking at the data now, there are 4 key drivers of profitability from a farming perspective. And the biggest one of those is sequestration rate. And I'm going to talk a fair bit more about sequestration rate. Secondly, there's the price of carbon. When most of the carbon methodologies that we're dealing with today were developed, the price of carbon was $23 a tonne. What farmers are ending up with now is closer to $10 a tonne. So the price certainly affects profitability, the cost of measurement and cost of doing projects, not just measurement but projects generally. And I know the discussion about small scale. That's the problem, is the overhead cost of doing projects. And the scale of project. And I'll talk a little bit more about that. Basically, we've got projects down now to around about 500 to 750 hectares. But whether that's viable or not depends entirely on the sequestration rate and the price of carbon. So we pulled together some data. This is from we've got a lot of properties. They generally average 3,000 to 5,000 hectares, the properties that are involved at the moment. We're working on generally budgeting on around about 0.5 to 0.75 of a tonne of carbon sequestered per hectare per annum. That's carbon, not CO2. And if we had a methodology that just discounted us by about 25%, you would net $5.34 per hectare per annum from doing a soil carbon project with that level of sequestration. Through Queensland, the average EBIT per hectare over the last 3 years from the grazing industry has been $41 a hectare. So that includes 2 years of high prices and 1 year of lower prices coming from our benchmarking work. So at a sequestration rate of 1 tonne per hectare per year, we're getting fairly close to about half adding about half the net income to a property. And if you got your sequestration rate up to 2 tonnes, you will make as much from carbon farming as you would from livestock production, that's beef. And certainly if we get the sequestration rates up around 5 to 7 tonnes, then you would become a carbon farmer first and a grazier second. And I'll come back to those sort of sequestration rates. However, we have a methodology at the moment that discounts what a farmer is likely to get anywhere from about 75 to 100%. And it is possible for the farmer to actually owe the government money at the end of 5 years after sequestering carbon. That is possible under the current methodology. Now, I don't know any farmers that are actually going to take that on. Why would they take on the risk? So not only that, they've got to wait 6 years for their income. So you've got to put money up front to baseline a property, go and implement the activities, which also has a cost associated with it. Go ahead and do that, wait, then pay for another cost to measure, and then wait for a payment. It's fairly risky when the mathematics do that to you. So it would mean that to have the same level of economics as you would with 2 tonnes per hectare, you would have to be sequestering 5 tonnes of carbon per hectare, which is really not reality when it comes to grazing land. So we've got a major issue with the methodology, and it's the discounting. And it's a discount on top of 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 a discount and on top of the last discount. And some of those are quite arbitrary. For example, there's an arbitrary 50% discount in there on top of the arbitrary 25% discount. And then there are other statistical discounts and other conservative ways of estimating in there as well. So unless that's sorted out, this is really not going to be a goer. One of the things, and there was a question yesterday about legumes. one of the things that we've found very recently that really is driving sequestration rates way above where we would have ever anticipated is legumes. This is a legume called Progardis, which is a desmanthus. And so that's the control. 2 kilograms of seed per hectare averaged, this is over 5 years, 4 tonnes of carbon per hectare per year. 4 kilograms of seed and 8 kilograms of seed, up around 8 kilograms of 8 tonnes of carbon per hectare per year. Now those results there look a little bit too good to be true to me, so we're actually going to redo those again this year. But it actually surprised us that level of sequestration. But it does indicate that it's possible to really increase sequestration rates. As I mentioned though, the downside for producers is the income is very, very lumpy. So a lot of money up front, and then that's a 4,000 hectare project, and then you wait 5 or 6 years, and then it's remeasured every 5 years, 6 years, and then you get your income after that. So, but there are a lot of benefits to producers in doing increasing soil carbon. So you get improved soil health, increased carrying capacity, water holding capacity. Enterprise risk hedge is a major one. For example, if I've got carbon credits sitting in my registry and I get a drought or low prices, I can pull my carbon credits out and still be able to put the kids through boarding school. And to me, it's a major way of evening out income in agriculture. And I can manage price and drought risk using carbon credits that I've got stored. Certainly going to increase ecosystem resilience. And you talk about adaptation, increasing soil carbon in agriculture is the major way to adapt to climate change. So a little bit of science and background on some of the stuff we've learnt. This is New South Wales data on growing a wheat crop. Any of you know anything about soils will know that a soil wants to maintain a carbon-nitrogen ratio of around about 12 to 1, roughly. And the biology will maintain that regardless of what you do to either the carbon or the nitrogen. The biology wants to maintain it something like that level. So if you're looking at half a percent organic carbon in your soil, it will require about 100 units of nitrogen to produce a 4.4 tonne wheat crop per hectare. But as soil carbon increases up to around about 3.5–4% organic carbon in the soil, you get to a point where you need no nitrogen to produce exactly the same crop. And probably the best practical hands-on real example I've got of that at the moment is one of my clients in South Africa on a dairy farm. The 6 years ago was producing 7 tonnes of dry matter a year under irrigation from ryegrass using 500 units of nitrogen. Today, this year, he's produced around 40 tonnes of dry matter per hectare and has used less than 50 units of nitrogen to do that. His water requirement has dropped by 20% to produce 6 to 7 times more dry matter. And his input costs have dropped substantially. Those guys, and there's a group of them in South Africa now, have done the same thing. Some of them have gone from 1% organic matter to 11% organic matter in their soils in 5 years. Now, most traditional science would tell you that that's not possible. Let me tell you, there are farmers out there doing this stuff. Now, what happens with soil carbon sequestration rate is that the rate of sequestration depends on how much carbon's actually in the soil. It bounces along the bottom at a fairly low sequestration rate until you hit a magic number of around about 1.7% organic carbon in the soil. When you hit that, the sequestration rate increases. Now, I asked this question of a scientist. I actually like asking of a lot of scientists. is there a limit to the amount of carbon that we can put into the soil? And every scientist will answer yes, it is somewhere around about 5-6% organic carbon, depending on soil. Some carbons go higher, some soils be less. But that's under the old paradigm where we think about percentages. In fact, there is no limit to how much carbon you can put into a soil when you start thinking tons of carbon, not percentages. Because once you've topped up a soil to 5 or 6% organic carbon, what happens then? What happens then? You start making soil. All you do is add more carbon. All right? So there is absolutely no limit to the amount of carbon that you can put into soils. And so most of our soils, agricultural soils, are right down here at 1% organic carbon. And so we need a lot of inputs. That extra carbon comes from fungi. The correlation between the fungal to bacteria ratio and the addition of new carbon in a soil, and this is carbon that is not in plant material. It is new carbon that's in the soil, is highly correlated to the fungal bacteria ratio. So it's fungi that are doing the job. Here's a little bit of real data from Gabe Brown, and some of you will have come across Gabe's work. So back in 93, he had about 1% organic carbon in his soil from conventional farming. He went into crop diversity for a few years, and his soil carbon went up to about 1.8%. He then went into a period of cover cropping. His soil carbon then went up to around about 2.5% organic carbon, and he is now sitting on about 6.5% organic carbon, and you can see that the rate at which that's happened has accelerated. Once he's cracked the 1.7% round or 2% organic carbon, the rate of sequestration has accelerated. He's actually sequestering carbon now at the rate of 24.7 tonnes of carbon per hectare per annum in a cropping system. Well, that's, as I say, this stuff is actually happening. One of the 10 minutes, thanks. So one of the things that's that we're playing around with a lot now, both internationally and here, is soil biology, and an approach that I only learned about last year called BEAM, which is biologically enhanced agricultural management. And this is this photograph here is this one is one year, so 6 months I think after applying biology to the soil, and there's a change in the carbon in that level there. We're down here after 2.5 years, so this is a year later, 2.5 years later, you can see what's happened, that carbon now is down 6.5 inches into that soil in only 2.5 years by adding the right sort of biology to that soil. So I could spend a day talking to you about the biology and all of the data that's behind that. So what are the steps involved in doing a carbon project? So we start with what we call a discovery process, and we find that it takes 5-6 months for farmers to get their head around what a carbon project is, particularly a soil carbon project. So what's involved? Is it feasible? What's it actually cost? How do you get paid? Who pays you? When do I get paid? What are my risks? All of those things people have to be very clear on before you go into a carbon project. So we capture a lot of data, we do a lot of mapping, we do some soil analysis, preliminary analysis to figure out what's there to start with. And then when we enter into a project to start actually measuring soil carbon itself, we go through a 5-step process, and I'll run you through very quickly a little bit of that. I'll run you through a project in the Burnett Mary that is underway, a soil carbon project. It's 5,239 hectares. That's the property, and each one of those red dots is where a soil sample has been taken. The colours are what are called CEAs, or a carbon estimation area. On this particular property, we have 33 carbon estimation areas, and what we've done is actually stratify the property. So each carbon estimation area is a particular land type, or a particular paddock, or a particular pasture type, because all of those things affect carbon yield and sequestration rate. And if we just randomly measured across that property, and I'll show you some data in a minute, the variability across there is tremendous. So if we just randomly measured that property, we would end up with very, very high variance. So stratification is a process of accounting for variance before we start. So that if we know then the variance in that colour there, for example, and we get a variance in there, and we get a variance in there, and a variance in there, they're different variances. And I'll show you the difference in carbon yield in that in a minute. So we head out with some fairly heavy duty gear. We're taking soil cores down to either 1.2 or 1.5 metres, and the cores come out intact, and they're encased in plastic. And the reason for that is that these soil samples are analysed in their entirety by scanning. So this instrument here, you can see it's mobile, so it's possible now to take the soil analysis gear into the paddock and analyse stuff while we're there. So these plastic encased soil cores go into there. We've got a doodad here that's a gamma. It shoots a gamma ray through the soil that measures the bulk density. We've got another instrument sits on top that measures carbon. We've got another one that photographs the entire process and the entire core, and a computer that captures all of that. And so what we end up with is we're actually able to measure bulk density and carbon. Well, we can do it in every 2.5 centimetres of the soil, but that takes a little bit too long. Generally, we do every 5 centimetres in the top 30 centimetres, and then we go out to every 10 centimetres. So we know exactly where things are in an entire profile. So we're not bulking up soils, and under the old process, we have to bulk these cores up. We end up with about 25 to 30 kilos of soil, which you then have to mix up and take 1 gram out of to analyse. That to me is bullshit in the technical terms, right? 5 minutes, right? I better speed up. So then there's a lot of number crunching to work out where our carbon is. So I thought I'd put up some percentages. So the highest percentage is in here, that particular CEA there, 3.12% organic carbon. That's in the topsoil. And over here, 0.6, 0.57% organic carbon. Topsoil is down to 30 centimetres in this data. And enormous variation across all of those CEAs. We put that into carbon yield, and the highest yielding CEA was this one here at 155 tonnes of carbon per hectare. The lowest yielding CEAs are these ones over here at 40 and 41 tonnes of carbon per hectare. So you can see there's 110 tonnes of carbon difference per hectare between our lowest CEAs and our highest CEAs. If we went out and tried to sample that entire thing without breaking it up into those land classes and that strata, we would have enormous variability in our data without knowing where that variability came from. So understanding that variability is critical. The other thing that's interesting that is a paradigm shift for a lot of people is there's more carbon below 30 centimetres down to about 1.2 metres than there is above it in tonnes. The concentration is higher in the top 30 centimetres, but the total tonnage in everywhere we've ever measured is higher below 30 centimetres than it is above. So we've got to be measuring to depth, and we've got to understand what's going on down deep. I won't worry about that, or I won't go into those. From the farming perspective, the thing that makes soil carbon work is the multiplier of carbon to carbon dioxide. So what you're putting into soils is carbon, What you trade is carbon dioxide, which has a multiplier that works in your favour, and that's what actually makes the sums stack up, because the amount of carbon you're producing is minute, very, very small, that you can put away each year. So I look at an ecosystem as a pie. With carbon at the centre of it, we've got ecosystem services, energy flow, biodiversity, soil health, water cycle that drive that entire ecosystem. For the last 150 years, we've been shrinking it. To me, it makes sense that if through mismanagement we shrink that pie, with real management we can reverse that and increase the size of that ecological pie. And we can do that on virtually any piece of land. Firstly, I think the most critical thing in increasing sequestration rate is management. It's the basis of doing any sort of project and improving ecological health. The second most important thing is soil biology. When I learned about soils 40 odd years ago, we only ever learned about chemistry and physics. Soil biology was never even mentioned. But we know today that soil biology drives physics and chemistry. You can change chemistry significantly in 1 to 2 years with soil biology. You can change the physics with soil biology. I think, well, I call them catalytic endpoints. I think we've got to get away from the old approach that we're fertilising soil. We've got to fertilise plants, and we've got to fertilise biology and look at what biology and plants need, not what the soil needs in big chunks. And again, I could talk for a long time on that, and legumes. So there's a whole lot of management systems that can be put in place in cropping, in horticulture and in grazing that will increase soil carbon sequestration and soil health generally. My belief is we've got to focus on soil health first, and productivity increases as a result of soil health. Carbon is the bonus at the end of that. So just in terms, that's grazing, you know, see what the rainfall did there. It's amazing how it goes along fence lines. You know, it all comes down to management. This is using compost extract, which is not compost tea, but compost extract on wheat in West Australian soils, which are basically a mixture of sand and salt. And you can see that wheat plant there. So there's the radicle, the seed, but look at that root system that's actually had biology applied to the seed and into the soil while that seed was planted. Look what that plant is doing. We now know from the research that the soil-plant biology interaction is highly intelligent. Between the plant and the biology, they know exactly where they need to partition energy and for what reasons. And you can see here the partitioning of energy there. This one's also interesting. There's a hard pan here. Now you'll see that the biology, so there's very little roots above that hard pan, but the biology has punched that root system right down through the hard pan in that cropping system for a recently germinated plant. Now in cropping systems, people talk about root-shoot ratios and trying to get the root ratio 1:1. The root-shoot ratio here is way, way above 1:1. And it's biology that actually achieves that. We talked about legumes a little bit. Leukemia, we've had the same sort of indications and results. Interestingly, we're getting about 1.2, about close to 2 tonnes of carbon per hectare in the leukemia rows, but in the grass between the rows, we're up around 3 tonnes of carbon sequestered per hectare per annum. I won't worry about that. Also, one of the other things that soil biology needs is oxygen. And I think that often one of the most important fertilisers that a farmer can put on soil is oxygen. Get air in there to get your biology functioning, and it can't function without it. So the last couple, the supply side risks, one of the biggest risks for a farmer is if you sign up to supply 100,000 tonnes of CO2 and you have a drought and you can't do it. That's a pretty big risk. Under our current contracts, you do not have that risk. So if you get a drought and you supply 50,000 tonnes, you're not liable for the other 50,000 tonnes. So that's a pretty good sort of contract to have with a fixed price attached to it. And if you're doing pasture projects, there's no risk of reversal while country stays in pasture. The new methodology now, which will be out later this year, will allow soil carbon to be done not only in grazing, but in broadacre cropping and in horticulture. So that now, by late this year, should be in place. Okay, that's it. We've wrapped up. Thank you.